Good morning, everyone. Well, no, good evening for you. Are we still? It seems we are complete for now. Well, there's no one joining at least. I received 3 questions on chapter 10, so I'll start by answering those. And then afterwards we can see if there are any more. Do you see the screen? Okay, good. So the first question was about the autocorrelation and what the link was with the correlation. Basically, I didn't go into details because it's not really important for this course, but we can quickly show the analogies. So a correlation normally is between 2 vectors x and y. And then you have the definition that the correlation between x, y is the covariance between x and y divided by the standard deviation of x, standard deviation of y, which is then, if you go to the formula, the sum of x minus x bar, or xi minus x bar times y I minus y bar over n minus 1 times sx sy. So this is the general formula. For the autocorrelation, there's one different, well, there is a difference that it's basically not 2 different variables, but you have the same variable epsilon. So in our case, we look at the residuals. So here in autocorrelation, this is between, in our case, epsilon and epsilon, but at different time points. So this means that this Sx and this epsilon, Sy, they will be the same. And each of them will be equal to the standard deviation of the residual. So here you will get S epsilon squared, basically. Then what you can show is that no, let's keep that in mind for a moment. I'll come back to that at the end. And then the second part here, this is the covariance formula, the one in green. This will correspond to this part. So if you now take a look at this formula, you have a sum. This time it will not be a sum over I, but a sum over the values k up to n minus tau for the lag. So xi is epsilon at time point tk. We know that the average for the residuals is 0. And then you get the same thing, but in tk plus tau, minus again the average of 0. And then you have to divide. You divide by, in this, wait, let's see this. So this n minus 1, this corresponded to the degrees of freedom. The degrees of freedom in the autocorrelation will not be n minus 1, but it will be n minus tau, because you have, because the lag between the points that you are looking at is tau. So you have the tk and the tk plus tau, and then you do this for n minus tau different terms of the sum. So the reasoning behind is a bit different. The correlation is very similar to the autocorrelation is similar to the correlation, but there are some differences because we are looking in a time series, and so we are looking at one variable at different time moments instead of 2 different variables. So we see now that the covariance corresponds to this green, and this green is called the autocovariance. Very similar to autocorrelation. And then what I noted is that this R epsilon should better have given another name, because it's a bit confusing. This is not the autocorrelation at lag 0, but this is the autocovariance at lag 0. So I would have been better to call it R prime epsilon, and then R prime epsilon can be shown, or R prime epsilon is basically this one. So here you take this formula for tau equal to 0, and then you see that you get the epsilon tk squared divided by n minus 0. So this is this formula, autocovariance for 0, and then it can be shown, but we're not going to go into those details, that this is equal to the variance of the residuals. And so you see that the correlation and the autocorrelation, they are very similar in formulation. The main difference is the degrees of freedom n-1 versus n minus tau. Does that sort of answer the question? Also for this part, the application of the simulation is more important than all the theory that we see. So you have to understand the principles, but there will, well, as you see also, there are no proofs. We just state facts, we explain why they are like that and how to use them, and then we apply them. Okay, so this was the first one. Because of that, you also see that if you look at the autocorrelation in 0, let's take another color. So this then would be, if you look at R epsilon in 0, this would be the autocovariance in 0, R prime epsilon 0 divided by this factor, which is basically just a normalization factor, so which corresponds to the variance R prime epsilon 0. You always see that the first one has to be equal to 1, which you also see in the plot here. So this first one, this is always 1. So you never consider this one. When you are looking between the boundaries, you only look from starting from leg 1 up to the final leg. And then the second question was, why do we have this distribution? So why is the autocorrelation normally distributed with mean 0 and variance 1 over n? That was a trickier one. So here, because we are looking at the data and we are looking at the actual data that we collect, this is the sample autocorrelation, not a theoretical one. And the way, so this one is normally distributed with mean 0 and variance 1 over n, so the number of observations or time points, basically. And what is being used there is another formula. So you know that the correlation is also the expected value. Wait. So you can also write this R epsilon tau is the expected value that I have to. Of x tk minus 0 times y tk. Sorry, I'm mixing things up. Let's start this over. And let's do it like this. So the correlation between x, y can also be written as the expected value of x times y over Sx xy. So this is another formula for the correlation. So basically the covariance is the expected value of x times y. if we do this for the autocorrelation, you get a very similar thing. So your autocorrelation R epsilon tau will then be the no, sorry, I'm one step ahead and I'm forgetting the means. So this is x minus mu x times y minus mu y. But since our means are 0, these will cancel out, but I'll write it anyway for now. So this is the expected value of our first variable was, well, let's immediately do it as epsilon at time point tk minus the mean of 0 times the second one epsilon tk plus tau minus the mean of 0 divided by, let's write it for simplicity as s squared of epsilon. So the variance, or well, yeah, we can even say it's sigma squared if we assume that epsilon follows a normal distribution with mean 0 and variance sigma squared. So this was our assumption anyway. This is also the expected value of epsilon tk times epsilon tk plus tau over sigma squared, because sigma squared is just a constant in the expected value. And then we will be using the central limit theorem. So central limit theorem that we saw was if x has a mean mu and a variance sigma squared, then x bar follows, if my sample size is large enough, a normal distribution with mean mu and variance sigma squared over n. We see now that this autocorrelation, this is an expected value, so this is a mean, and we can just use the central limit theorem to calculate the distribution of this mean. And then we go to the mean or the expected value itself. So here what we get according to central limit theorem would mean that the autocorrelation, this follows a normal distribution if my time points are large enough. So if I have a large enough sample with as mean the expected value. So in this case, let's say this is now my variable. So this is the variable that corresponds to this x, and we are looking at the average of this variable. So we have that the mean of my autocorrelation will be the mean of the thing in yellow, the expected value of epsilon tk times epsilon tk plus tau over sigma squared. And the variance will be the variance of the yellow thing. So epsilon tk plus tau over sigma squared divided by the number of points, so divided by capital N in this case. And now we have to calculate the mean and the variance. So the mean, this one is easy. The expected value of a product is just the product of the expected values. So this is expected value of epsilon tau k times the expected value of epsilon tau k plus tau over sigma squared. We know that the expected values are 0 because they are white noise. Epsilon, the residual, is assumed to have a mean 0. So this is 0 times 0 over sigma squared, which is 0. For the variance, let's just look at the upper part. So just do this and keep in mind that we have to divide by n. So we will calculate this one. The variance, so we have the variance of a random variable times a random variable divided by sigma squared. Sigma squared is a constant, so we can take it out, but it will get squared. So it gets 1 over sigma to the power 4 times the variance of epsilon tk times epsilon tk plus tau. And then we have to use a property of a variance of a product. So we did not see that, and the details are not really important, but we know, or we can prove that the variance of x times y, so we have here epsilon tk, the first variable, times epsilon tk plus tau, the second variable. This variance is the variance of x times the variance of y if and only if mu x is mu y is 0. So if the means are 0. But for our residuals, the means are 0. So we can apply this formulation. So this would then be 1 over sigma to the power 4, the variance of epsilon tk, times the variance of epsilon tk plus tau. And then we know that for this, the variance is sigma squared for each of them. So it's 1 over sigma to the power 4 times sigma squared is 1. And so here, this one becomes 1 over n in total. So that's the reason why our autocorrelation follows a normal distribution. Based on some central limit theorem. So if my sample size is large enough, but in practice, we will just use it as if it should be large enough. So normal distribution, mean 0, and variance 1 over n. But basically, that was a question which was not meant to be in the purpose of this course, because it's a bit too far for this part, but it was a good question anyway. And then the final one I got was on slide 82. So here, the Fisher information matrix. So the question was, is the purpose of the Fisher information matrix getting an idea about the structure or the variance structure in the data? And the answer there is basically no. It's not for the variance of the structure in the data. It's for the variance of the parameters estimation. So what you have is that this Q in the formula, this is the covariance matrix for my data or for my measurement errors, which correspond to or which are directly coming from the data. The Fisher information matrix, or at least the inverse of the Fisher information matrix, so FIM minus 1, this will give me information on the covariance structure of the parameter estimations. And not on the data itself. Because if we go back, what we had was we were trying to calculate a confidence interval for the parameter estimation. So we were looking for a confidence interval for this tau hat. We needed this CH minus 1, which depended on the inverse of the Hessian. The inverse of the Hessian was not always, or was often not calculable because of different reasons. Columns which are, I forgot the correct word. So linearly dependent, or sometimes it can happen that they are not linearly dependent in C, but because of computer precision, they are rounded, and then you get problems with the division. So often this one is very difficult to calculate. And so what you do is you replace this value. So you could say that this can be approximated by the inverse of the Fisher information matrix, approximately. That's why we calculate the Fisher information matrix. So it gives you the inverse of the Fisher information matrix, gives you some idea about the covariance structure of the parameter estimation, so of the thetas, but not of the data itself. If that makes sense. Good. So those were the questions I received. Are there any other questions? So it's about linear regression. When the model is transformed, we check for the independence assumption. Should we have to deal with original data or transformed data? Transformed data. But for the independence assumption, normally it won't matter, because if the original data are independent, then the transformed data will be independent as well. So for independence, it doesn't really matter. But normally you check everything on the transformed data once you do a transformation. Question. The partial F-test in chapter 7. So I do not have the slides of 7 uploaded anymore, because we've had two Q&As on that one. But the reduced model and complete model is basically what it says. So you have, very generally speaking, a model y is x1 plus x2 plus x3. So with x1 plus x2, x3, I just mean that they are a linear combination of these three variables. So alpha x1 plus beta x2 plus gamma x3 plus a constant. If this is my complete model, then a reduced model is, for example, x1 plus x2. So basically, the reduced model will be a part of the full model by taking one or more variables out. But you have to have an overlap of the variables, just less than the total. So the complete model is everything in it. The reduced model is the one, or is the model or the same model with some one or more variables out. And where we use it is mostly with dummy variables, because with dummy variables, it doesn't make sense to look at the p-values. An outlier is I'm confused about the difference between extreme leverage and outliers. Why are they different? Because a leverage is a measure and an outlier is a point. Leverages give an idea about which points might be outliers, but they are a way to calculate, so they are a measure. They are not one of the data points themselves. No. So in the results part of the project, do we need to make the table? So it's maybe easier if you write questions, that you do them to the group so everyone can read them. But the other one was, in the results part of the project, do we need to make the table that includes all the model TP values? Or can we just make a table with the selected models in each step? It's the selected models in each step. So you don't have to include all of them, only each of the models that you kept in each of the different steps. So you can see the progression of how the model evolves. Otherwise, the table would become quite large. If the data is an influential observation, can I then say that the data are also outliers at the same time? In our sense, we say yes. So I used both terms quite interchangeably, as influential and outlier, but it depends on how you define an outlier. So sometimes an influential observation is not really an outlier. because it still fits the data sort of. So so if this is my data set, you could have a point which is here, which is in a sense outlying, but if this difference is not too large, we usually call it an influential observation, but not an outlier, because it lies within the range of the x values, the normal x values. So there's no difference in this, it falls between those, and it also falls between the range of the y values. So it's in the range of the x values, it's in the range of the y values. So it's not really outlying, but it will still be influential because it does not follow the main part of the data. But in our lectures, I used both terms quite interchangeably. So you can also define this as an outlier because it's quite different. But usually outliers, they are farther away, so they don't fall in the range of one of the variables. Any other questions? Cool. Wait. So first one, is it possible that the data have extreme leverage value, but when we plot the graph, the data is not far from the bulk of the data? I should check. I don't know by heart, but it can be. Well, it depends on what you define as not far from the bulk of data. So this point could have an extreme leverage value, I think. And then the question is, what do you call not far away from the bulk of the data? So it's a bit a difficult question, but I will check and I will let you know. So that's this one. Do we have to establish linearity between the outcome variable and the predictor variable before we make the model? So yes, that's easier. Otherwise, you will see in the residual plot that there is no linearity and you have to start over. So yeah, you can. So that's also why we ask in the project to check the, or why you do an descriptive statistics at the beginning, and you look for the relation between the explanatory variables and the predict or the outcome variable, where you and then you can see if there is a linear relationship, yes or no, and if not, you can already try to make some corrections to that. So it's easier. It's easiest if you first check linearity and then start model building. Otherwise, you do things 2 times. Can we consider that all of the influential points are outliers? Technically, they will not be. So I don't remember the videos exactly. I tried to pay attention of not confusing them too much and use influential points. but I think I mixed up sometimes, so that's why I also said I use them a bit interchangeably. But if you look at it very very strictly, then you will have influential points which will not be considered outliers, but they will most likely be on the border of being outlying. But for me, for our course, you can consider them to be the same. So mostly, if you have an influential point, it will be an outlier. But it's theoretically not necessarily 100% the same, an influential point and an outlier. Good. Any other questions? If there are not, then I wish you all a good start of the week. It's not on Friday this time, it's on Monday, sorry. So a good evening, and then a happy might not be the right word, a good week. And then for next week, we won't. So this week, next week you have the exams. And then the last classes are in the week after the last week, I think. So you have your exam week, yes. So next week I'll leave you be. And then we will meet again the week after your exams with the final classes and some Q&As. Good luck with the exams then also, by the way. And then I'll see you in 2 weeks.